All right, welcome back to the second video in our series of videos on improper integrals. In this video, we're going to look at the type 2 integrals. So this is the second kind of problem that can happen when you want to integrate a function. And these are functions where there's not necessarily something wrong with the interval itself, but there's something wrong with the function in that it's badly behaved. And the most common bad behavior is an infinite discontinuity. So the function is shooting up to infinity or shooting down to minus infinity somewhere where you want to integrate. And it may not seem like it, but actually these type of integrals show up in a lot of different applications because you have functions that oftentimes when you're kind of dividing by zero or something, you have functions that are just shooting up to infinity, but you're still interested in summing them up. You're still interested in integration. So we're going to look at this kind of situation. So a good example of this is this integral here, the integral from 0 to 4 of 1 over square root 4 minus x. Now, the only problem here happens at 4. So from 0 all the way up to 4, but not including 4. If you go to just a little bit before 4, you're going to be okay. You're going to be taking the square root of a positive number in the denominator. It's perfectly well defined and everything. But at the end point, it's not. And also, as you approach that end point, the function blows up. So you can't just say, oh, I'll just define it at 4 and whatever, because if you define it at 4, now you've made it a discontinuous function. And so the original definition doesn't necessarily apply. So what are we going to do in this case? Well, what we're going to do is kind of the same idea we did with the type 1. We're going to approach that problem as a limit. We're going to say, okay, we can't go out to 4, but let's go out to t, and then evaluate it in terms of t, and then take the limit as t approaches that problem point and see if the limit exists. And if it does, we'll say that the integral converges. And if it doesn't, we'll say it diverges. And that's the best that we're going to do with this. And there's a number of different cases that can come up here. You can have the discontinuity at the left endpoint, at the right endpoint. You can have it at both endpoints. You can have it at a point that's in the middle of the interval. You can have all of these. The worst possible case, you could have the infinite discontinuity at both endpoints and maybe a couple points inside the interval. So there's a lot of different cases, but there's one general principle that you can remember for both the type 1 and type 2 improper integrals, and it's the following. Whenever you have a problem, whether it's with the interval itself or with the integrand, simply cut it away. Make an excision, remove the problem, and then get as close to the problem as you can. Make an approximation, and then calculate an appropriate limit to approach that problem. And the value of that limit is going to be the improper integral. It's a simple idea, but it encompasses all the different cases, both in this video and the previous one. All right, so we do need to state these definitions. So let's start with the first case, which is if there is an infinite discontinuity at the right endpoint. So we're going to suppose that f is continuous on the half-open interval from a to b, including a, but not b, and discontinuous at b. Then we're going to define the integral from a to b. Now, this notation kind of hides the fact that it's an improper integral because it looks just the same as it would a regular integral. So you have to be aware of this. If you don't see infinity, look at the integrand and make sure, wait a second, is there something going on here? Is this just an ordinary continuous function that we're integrating like normal? Or is this an improper integral because it has a discontinuity? In this case, this notation a to b is really going to be defined as the limit as t approaches Now, what we're going to do is approach the problem at B. So we're going to approach B, but notice we're only approaching it from one side. So this is a one-sided limit. And here we're approaching B from below. So this is going to be a left-hand limit. So the limit is t approaches B from below or from the left of the integral from a to t of f of x dx, provided, of course, again, the limit exists as a finite number. A similar definition is going to happen if the problem is at the left endpoint. Just kind of switch everything around. In this case, because the problem is at the left endpoint A, we approach A from values a little bit bigger than A. So this is a right-hand limit. So it's also a one-sided limit, but it's a right-hand limit, not a left-hand limit. And the third case we're going to consider is if it has a discontinuity at both the left and the right endpoint. So what are we going to have to do there? So in this case, let's suppose f is continuous on the open interval, continuous on the open interval from A to B, and discontinuous at A and B. And we're also going to say then for some C between A and B, both the integral from A to C and the integral from C to B exist. Now notice these A to C and C to B, because there's discontinuities at A and B, these are not ordinary integrals like you had in Calc 1. Again, these are the improper integrals that we just defined in parts A and B. So these are two improper integrals, and we're saying if you have the discontinuity at both endpoints, then you have to split it up and actually add two improper integrals together. Now, there's also the issue here that you could say, well, what if somebody chooses a different C than I do? What if they split it up a different way? And you can show that it's also independent of C. So I'll just put it in parentheses here. Independent of C in the same way that it was when we had the integral from minus infinity to infinity. Okay, so basically the same kind of argument. Last thing, what if you have a discontinuity in the middle of the interval? So if f has a discontinuity at C, where C is between A and B, and both of these exist, so A to C and C to B exist, then again define it to be the sum just like above. Again, note that that integral from A to C and the integral from C to B in part D, it's different than the ordinary integral from Calc 1, and it's different from the integrals in part C, because the problem is on the other side. It's on the other endpoint. So, you know, this is the thing about the notation. You have to think about what's actually going on with the function, where the problem is, and what kind of limit you're taking, especially with these type 2. Type 1, it's not as easy to get mixed up because it's right there. It's infinity or minus infinity. But with these ones, you do have to be careful. And think about if you had at both endpoints and in the middle, how you would have to split that up. You would really have to split it up into 1, 2, 3, 4 different integrals, because you have to approach the endpoints by an integral, and then the one in the middle you'd have to approach by 2 integrals, because you have to do each side separately. So again, think about the general principle of wherever there's a problem, approach it as a limit, whether you have to do it as a one-sided limit or a limit as you go out to infinity or minus infinity, and then just add them up. And lastly, we just say here again, if any of these integrals exist, if any of these improper integrals exist, then we say that it converges. And if they don't exist, then we say that they diverge. All right, let's look at some examples. Okay, we'll start with the example that I already talked about earlier as an example, this integral from 0 to 4, where the problem is at the right endpoint at 4, the integrand is blowing up. So we're going to define this as the limit as t approaches b from, well, when b here is 4, so as t approaches 4 from below of the integral from 0 to t of dx over square root 4 minus x. Now, to integrate this, I think the easiest way to do this is just to recognize this as 4 minus x to the negative 1/2 power. Because 4 minus x to the negative 1/2 power, that's just a little u substitution with -1. So you're going to pick up a factor of -1. You can just do the power rule as normal. So this would give us the limit then as t goes to 4 from below of 4 minus x to the 1/2 over 1/2. So that would be 2, 4 minus x to the 1/2. But we pick up that minus sign because of the substitution. And it's all of this taken between 0 and t. If that was kind of a little fast to go through without writing out the substitution, you can write it out, or you can just check by differentiation just here. -2 times 1/2 is -1, so you get -1, 4 minus x to the negative 1/2. The chain rule, you get another factor of -1 that cancels the -1. When I evaluate this, I'm going to get, well, so what I like to do with the negatives, I often will switch the limits and change the negative. So that'll give me 2 times, that'll be 4 minus 0 to the 1/2. So 4 to the 1/2 minus 4 minus t to the 1/2. Okay, now as t goes to 4, 4 minus t goes to 0. So this entire variable term here is going to 0. We're just going to be left with 2 times 2. So this is going to have limit 4. Okay, let's look at our next example. Our next example is going to involve a trig function. So what is the integral of tangent from 0 to pi over 2? Again, make sure that you understand why this is an improper integral. It's because in the graph of tangent, you think about the graph of it, it has vertical asymptotes at plus minus pi over 2. So from 0 to pi over 2, it shoots up like this. Okay, so we're asking basically, what is the area of this stuff right here? So to do this, we have to, again, use a limit as we approach from below. The problem is at pi over 2. So as t goes to pi over 2 from below of the integral from 0 to t, tangent theta d theta. You need to remember what the integral of tangent is. This is one that you can think about substitution and do, but really it should be just committed to memory. The integral of tangent is natural log of secant. Now, normally it would be natural log of absolute value secant, but because the secant is always positive between 0 and pi over 2, we can just say ln of secant. So we're going to be evaluating ln secant from 0 to t. So that's natural log of the secant of t minus natural log of the secant of 0. So now you have to think about a little bit of trig stuff. The secant of 0, the cosine of 0 is 1. That means the secant of 0 is also 1. And then the natural log of 1 is 0. So actually, this entire second term here, this is all just 0. So really, it's just the natural log of the secant. Now, what happens to secant as t approaches pi over 2 from below? I'll give you a minute to think about that. Think about the unit circle or think about the graph to get where this goes. So as we approach pi over 2, secant is actually blowing out because it's 1 over cosine. The cosine of pi over 2 is 0. So secant is actually approaching plus infinity as t approaches pi over 2 from below. And that means that the natural log of that, the natural log of something blowing up to plus infinity, is also going to approach plus infinity. So this is going to diverge. So let me kind of write that out here. This is saying as t approaches pi over 2 from below, cosine approaches 0 from above, so secant approaches plus infinity, and natural log of secant also, I don't know why I put another parentheses there, this also approaches plus infinity. So this diverges. All right. One more example, and this is an important example because it illustrates a common mistake that people will make. So we're going to integrate 1 over x minus 3 from 1 to 6. Now, at first, when you look at this, you're like, wow, this looks like a pretty simple integral. Doesn't look very complicated. But notice the interval from 1 to 6. If you notice, that's not defined everywhere. X minus 3, if I plug in 3 there, I'm dividing by 0. So in fact, I have an infinite discontinuity at 3 here, and I need to split this up. So the first thing I need to realize is that this has got to be split up at that discontinuity. So I'm going to have to integrate from 1 to 3. And then add to that the integral from 3 to 6. And I have to do each of these separately and then put them together. Since I'm going to be integrating 1 over x minus 3, let's just kind of do this on the side. I'll just kind of make it a little divider here. The integral of 1 over x minus 3 is natural log of absolute value x minus 3 plus c. Now, I do need to include the absolute value here. And the reason is from 1 to 6, x minus 3 might be positive or negative. So it will depend on which of these integrals I'm evaluating, how that absolute value actually gets evaluated. So first, let's look at the integral from 1 to 3. So this is the limit as t approaches 3 from below, integrating from 1 to t, dx over x minus 3, which is the limit of natural log. Now, between 1 and 3, x minus 3 is negative, which means this is going to actually be a negative number, which means the absolute value of x minus 3 is going to be 3 minus x. Okay, so I'm going to write this, instead of writing it as ln of absolute value x minus 3, I'm going to write it as the ln of 3 minus x. And this is going to be between 1 and t. So this gives me limit of, let's see, natural log 3 minus t minus natural log 3 minus 1, so that's 2, minus natural log 2. Now, what happens here? As t approaches 3 from below, let's be super careful here. as t approaches 3 from below, minus t approaches -3 from above, which means 3 minus t is going to approach 0 from above. So this is approaching 0 from above. Think what happens for the logarithm. You get that the logarithm shoots down to minus infinity. Okay, remember the graph of the logarithm? Okay, the graph of the logarithm is like this. So we're looking at this piece here. This is shooting down to minus infinity here. This is 1. So overall, this entire term there is going to minus infinity, and then subtract ln 2. That doesn't affect it. So this is definitely diverging. Now remember, this was just the integral from 1 to 3. We haven't even done the integral from 3 to 6 yet, but it doesn't matter. In order for this integral from 1 to 6 to converge, both pieces have to converge. As soon as you find one piece that diverges, we're done. We don't even have to look at the other one. So we get this integral diverges. Now, what was this mistake that I said people would make? It's very tempting when you look at this integral to just go into your Calc 1 mode, like you're back in first semester calculus, and just do the natural log and plug in like the fundamental theorem of calculus. So let's see what happens if you do that. If we neglected to notice the infinite discontinuity and we just applied the fundamental theorem, we would get an incorrect calculation. Here's what would happen. We would find the antiderivative of the integrand, which would be natural log of x minus 3. So that is the antiderivative, but you're just not allowed to use it with the fundamental theorem here. So here's what you can't do. So that's the problem. Notice that if we do go ahead and do it, we will get natural log of 3 minus natural log of 2. So that'll give us natural log of 3/2, which is definitely not correct. Okay, so just be aware of that. So that's a problem that professors and instructors will love to throw on an exam just to see if you're paying attention, that you recognize when you need to take an improper integral and you can't just do it like Calc 1. All right, one last example. And all the examples we've done so far, we've kind of focused in on the improper integral part, right? Because that's what we're learning about, where you want to get familiar with what is a type 1 improper integral, what is a type 2 improper integral, how do you set them up, what's the definition. But remember, for a general problem, it could be an improper integral, and you might need to use integration techniques, and there's stuff that you learned in Calc 1 as well. So this is an example of one where it's an improper integral, but there are a lot of integration techniques involved here. So let's look at this. We're going to integrate 1 over square root w squared minus 9 from 3 to 9. So the problem here, it looks like maybe 9 is the problem, but it's w squared. So the problem's actually at 3. It's blowing up to infinity as we approach 3 from above. So we need to do this as a limit. It'd be the limit as t goes to 3 from above. We're integrating from t up to 9 dw over square root w squared minus 9. All right. Now, what is the integral of this? Well, there's a couple ways you could go. You could just look this up in a table of integrals. But this is in most table of integrals, even short tables. For instance, ours from the book, which is a very short table. It's only 150, 200 integrals, which is very short. It's number 43. So you could do this, number 43 from our table. But let's say that you didn't have that, you didn't remember it. We can still use integration technique. This is one of those quadratic forms, and so we can do a substitution, a trig substitution. So we're going to let the trig substitution, we want w to be 3 times secant theta. If you remember about the 3 different types with sine, tangent, and secant, this is the one where secant is the appropriate one. So w is 3 secant of theta. dw is 3 secant tangent d theta. All right. And we have to draw a triangle for this. So here's going to be my triangle. If w is 3 secant theta, that means secant theta is w over 3. So that's w over 3, which makes this side length w squared minus 9 in square root, which is the expression we have there. So good, that matches. And so when we integrate this, let's just do this completely on the side. So we're just going to kind of put a line here. I just want to find the antiderivative of this. Okay, so dw. So on top, I've got 3 secant tangent d theta. And in the denominator, I've got square root of w squared, which would be 9 secant squared minus 9. Okay, so we need to clean this up. On the bottom, we can factor out the 9 from under the square root, and that would make a square root 9, which would cancel with the 3 on top. Okay, so I'm going to cancel that. So that's going to give us secant tangent d theta on top. And then we've got square root of secant squared minus 1. Secant squared minus 1 is tangent squared. So we've got square root tangent squared. Now, square root of tangent squared normally would be absolute value tangent, but if you remember what I talked about earlier when we were doing these kind of substitutions, I said that if you choose the domain restrictions right, it's just tangent. So we're going to just be able to cancel the tangents here. And we're integrating secant. Which, again, this is one of those strange integrals that you really should just commit to memory. It's the natural log of absolute value secant plus tangent. So ln secant plus tangent. Of course, we do have to plug back in. Now, secant we have here is w over 3. Well, what's the tangent? Well, this is what the triangle is for. The tangent is root w squared minus 9 over 3. So we get natural log of w over 3 plus square root w squared minus 9 over 3. Notice that I can rewrite this as the natural log of 1/3 times w plus square root w squared minus 9. The reason I'm doing this is if you were to use this number 43 from the table, it's very interesting that you wouldn't get natural log of w over 3 plus square root w squared minus 9 over 3. You'd actually just get natural log of w plus square root w squared minus 9. And this is something I mentioned in class earlier. When you're anti-differentiating and you get just a natural log of something, because antiderivatives are only determined up to a constant, the product rule for natural logs, or for any logs really, you can break apart that product. So really what we have here is natural log of 1/3 plus a natural log of the w plus square root w squared minus 9. But natural log of 1/3 is just a constant. And we're finding antiderivative, it's only determined up to a constant, right? It's plus c. So we can just ignore that 1/3. So when you are integrating to get a function, an indefinite integral, you can always ignore constants inside a natural logarithm or inside any logarithm. That's almost always natural logarithm. So I'm just going to ignore that 1/3. All right, so that was integrating just on the side here. But we still have to actually complete the problem now. So let's go ahead and do that. Okay, so we're looking at this limit. So it's the limit as t goes to 3 from above of, so I'm going to be evaluating this from t to 9. Okay, so I'm going to be evaluating this from t to 9. And because everything inside here is going to be positive, I'm just going to use parentheses instead of the absolute value. T to 9. All right, we have just enough room to finish this off. Oh, we got plenty of room here. All right, so that's natural log of 9 plus square root of, let's see, 81 minus 9, 72. And then this is subtracting a natural log of t plus square root t squared minus 9 as t goes to 3. Now, we can just plug in 3 here because this function is going to be continuous, the second term here. So it's going to be the limit. Remember that square root 72 is 6 root 2. So it's the limit of ln 9 plus 6 root 2 minus ln of 3 plus, oh, that's just going to be 0, right? 3 squared is 9, so that's just going to be 0. Okay, plus 0. So that means there's no limit now. It's just a number. So it's natural log of 9 plus 6 root 2 minus ln 3, which if you left it like this, honestly, I'd be very happy. Very happy. But we can do a little cleanup on aisle 5 because these are logarithms. We can put it together as 9 plus 6 root 2 all divided by 3. That's the quotient rule. And then if you cancel out a factor of 3 from every term, we get natural log of 3 plus 2 square root of 2. And that is the final answer. That is the value of this integral. So that would be the area under the graph of that curve. Natural log of 3 plus 2 square root 2. So I think this was a really good example of an improper integral that required some integration techniques, or actually required some kind of integration in addition to the fact that it was an improper integral. All right, so there's one more video we're going to do on improper integrals, and it has to do with comparison tests. Now, the idea behind a comparison test is not to evaluate the integral, it's to determine merely whether it converges or diverges, which often is important to know regardless of the value. So that's the last video, and that will wrap up everything with these improper integrals, and then we're going to move on to some more applications after that.